Okay, so I want to say a little bit about normalization. So this is our normalized quantity. So this is small for z f of x with z not close to integer. If xz over 2 to the 2L is roughly, well, d plus 1 over 2 to the 2L. So it's very close to an integer. Xz if, no, this is supposed to be rz. Well, this thing, there are roughly r copies of, there are 2 to the 2L over r elements in the sum. In sum, if they're all pointing in the same direction, if all in roughly same direction, which recall from this this intuition picture of the unit circle is when we get a large thing, the sum is 2 to the 2L over r. So probability is roughly, well, we take this, we multiply it by 2 to the 2L over r. 1 over 2 to the 2L, 2 to the 2L over r squared equals 1 over r squared. And there are possible values of f of x, because f of x was periodic with period r, which means there are things in the range, and there are also possible values of 2 to the 2L over r times d, with d well, okay, so I want to say all our possible values of d to the 2L over r, which are less than 2 to the 2L. So this is the output of the function, which was z. And what really happens, although I'm not going to have a chance to prove it, is you can look at the values of z between 0 and 2 to the 2L. There's one spike at z equals 0. There's a spike at 2 to the 2L over r. There's a spike at 2 times 2 to the 2L over r, etc. And away from these spikes, it decays like, if you're distance k from one of these spikes, it decays like 1 over k squared from the amplitude no, sorry, the probability is 1 over k squared from the top of the spike. And all of these spikes have the same, if you integrate over any of these spikes, it gives you the same probability. So this is what actually, what you see, or the probability distribution of what you see when you measure z. And it doesn't really depend on which f of x you get, although it might by a very tiny amount. So that's the algorithm. Are there any questions? Yeah?
So where do we get the log squared dependence?
Okay, so, okay. So what was the algorithm? It was, first thing was a black box for the function f, which we're assuming takes constant time. Then we have a quantum Fourier transform. Remember, if we had the quantum Fourier transform on n bits, it took n squared gates. N squared gates exactly. And it's something like n log n. Well, actually, it was n choose, n plus 1 choose 2 gates exactly. And it was O of n log n to do an approximate Fourier transform that's good enough for to get the results of the algorithm. So that's log n squared. That's where you get the log n squared problem. When you're doing the factoring, this term, computing the function, actually dominates the quantum Fourier transform, so we don't need to worry about that.